chromatography (GC) is a common type of chromatography used in analytical chemistry for separating and analyzing compounds that can be vaporized without decomposition. In gas chromatography, there is a mobile phase which is a carrier gas, such as helium, nitrogen and argon. And there is stationary phase, called a column, which located in an oven where the temperature of the gas can be controlled. There is also a detector that measures analytes in a gas stream attached to the GC system. The flame ionization detector is almost universally employed, where the flame commonly is generated with hydrogen and air. The auto-sampler provides the means to introduce a sample automatically into the inlets. Also, manual insertion of the sample is possible. The column inlet, or injector, is attached to the column head and provides the means to introduce a sample into a continuous flow of carrier gas. In the injector, a sample is introduced into a heated chamber via a syringe through a septum. The heat facilitates volatilization of the sample and sample matrix. The carrier gas then either sweeps the entirety, splitless mode, or a portion, split mode, of the sample into the column. In split mode, a part of the sample carrier gas mixture in the injection chamber is exhausted through the split vent. In splitless mode, all the sample carrier gas mixture in the injection chamber is transported through the column. Two types of columns used in GC: packed column, where the stationary phase is coated directly in the column, and capillary column, where the stationary phase is coated with the inner wall of the column. The mixture separation is based on differential partitioning of the components between the mobile and stationary phases. The component which has less affinity to the stationary phase, consequently less interaction, travels faster and eluted out first. And the component which has more affinity to the stationary phase, consequently more interaction, travels slower and eluted later. In addition, other factors influence the separation of the components, such as column temperature, carrier gas flow rate, column length, and amount of material injected. As compounds elute from the column, they interact with the detector. Different types of detectors can be used, such as the flame ionization detector, thermal conductivity detector, and mass spectrometer detector. The operation of the flame ionization detector is based on the detection of ions formed during combustion of organic compounds in a flame, which generated by hydrogen and air. To detect these ions, two electrodes are used to provide a potential difference. The positive electrode doubles as the nozzle head where the flame is produced. The other, negative electrode, is positioned above the flame. When an organic compound is mixed within the hydrogen flame, mainly carbon ions are generated. And a current is produced between the electrodes proportionally to the amount of organic compound present. This current is measured with an electrometer, amplified into proper voltage, and fed into an integrator. The manner in which the final data is displayed is based on the computer and software. The number of peaks present can indicate how many components are in the mixture. Usually, the x-axis of the gas chromatogram shows the amount of time taken for the analytes to pass through the column and reach the FID detector. Typically, the y-axis, or the area of the peak, is a reflection of the amount of a specific analyte that's present.